Welcome, Professor Vaibhav. I'll start with a short introduction about Professor Vaibhav. He's an assistant professor in the Department of Electrical Communication Engineering and a full-time associate faculty member of the Robert Bosch Center for Cyber Physical Systems at the Indian Institute of Science, Bengaluru. He was a postdoctoral scholar in the Department of Mechanical Engineering at the University of California, Riverside from 2017 to 2019. He received his MS and PhD degrees from the University of Notre Dame in 2012 and 2016, and bachelor's degree from the Indian Institute of Technology, Kanpur in 2007, all in electrical engineering. So thank you, sir. Thank you very much you being here today, and over to you, sir.
Okay, thanks for the introduction. I hope I'm audible, my slides are visible, and my video is also, my video feed is also visible to you, right?
Yes, sir, perfect.
Okay, so yeah, I'm delighted to be a part of this summer school, and I'm happy to give a talk on this fine morning. So I think we had a very nice session in the morning, so I hope you will also gain and benefit from this next coming sessions. So by the way, my internet connection might be a bit unstable. So if that happens, please let me know. I can switch over to another network. Okay. All right, so let's begin. So this session is all about intersection of two different fields. The first field is the control theory, control systems, and the second field is the communication systems or network communication networks. So basically, these two fields, I think you might be aware of these separately, right? You might have taken courses in control systems in your undergrad or master's or PhD. And similarly, people from communication background have taken courses and worked in these separate areas. But what I want to give you a main message today is that there's a very nice area which deals with the intersection of these two diverse fields. And that is the field of network control systems or control over networks. So the agenda of this talk is to give you a brief overview of this field, the kind of results that we will see two different results that will motivate you on how these two fields come together, and to give you an idea of what kind of problems are possible when these two diverse fields come together. So that is the overall agenda of this next lecture. All right, so let me begin. So let me begin just by mentioning how did the control technology evolved over the past 2 or 3 centuries. So it really started in the 1780s during the Industrial Revolution, and the steam engine by James Watt was the first main control system that was developed to control the amount of steam that was injected in the engine. Then moving forward in 1940s during the World War II time, there was again a need to develop control theory or control systems for aircrafts and for controlling the guns and the radars. And then we move forward to the space age in 1960s. And there also, it was a space race between US and Russia, and therefore it led to a lot of development in control theory. So as opposed to World War II, where we focused or people focused mainly on frequency domain methods, in the space age, people moved from frequency domain to time domain methods. So that was the big difference. And then moving forward in 1980s, basically people developed industrial control applications. So suppose you have a process plant or a chemical plant and you want to monitor the different processes, you want to control the different flows going into the plant. So for that purpose, this PLC control or industrial control was developed. And finally, we see that nowadays we have a lot of smart things, right? We have smart cars, we have smart grids, we have smart cities. So now these systems are much more intelligent as compared to previous systems, and this is the future. So we are using control techniques, we are using machine learning techniques to do intelligent control. So this is a very brief overview of how the control technology evolved over the past 2 or 3 centuries. So why I'm telling this? Because so in the audience, I assume people are more familiar with the communications background, right, and less familiar with the controls background. So that's why I just gave you a brief overview of this. Now, moving forward to the communication part, I think most of you might be aware of this. So you can look at the internet evolution or the evolution of mobile networks or wireless LAN, right? So in the internet, we started with ARPANET, which was in 1970s, developed by the US agencies, and then it evolved into the NSFNet, and then using TCP/IP protocols, internet was developed, which we use currently. In mobile networks, again, we started with 1G, 1980s, and fairly after every 10 years or so, we have new standards. So going from 1G until 5G, right? So now we are even talking about 6G in the coming future. And for the wireless LAN, again, the first wireless LAN was developed in 1971, AlohaNet, and then there was a bit of a gap. And then beginning from 1997, when 802.11 was introduced, then roughly every 5 years, we have new standards, right? And now we have 802.11ax. So these are the brief evolutions of control theory and communication theory. So now what happened is that previous to year 2000, these two technologies were evolving somewhat independently, right? People were working in these different fields independently of each other. But during 2000s, during the last 2 decades, there is a renewed interest in combining these two different fields. There were results previously also, but this last 2 decades gave really a new boost to this field. So essentially, you can say that communication meets control. So, and it was also basically developed because of the different applications that were coming into picture, right? So here I have mentioned some applications. So if you look at remote surgery, it's a very nice and classical example of control and communication coming together, right? So let's say there is a remote surgeon who wants to do a remote surgery. So he wants to control the movements of this robotic surgeon, and the data transmitted is clearly over a communication channel or a communication network. So therefore, interesting problems arise on how does the control performance is affected by the communication channels. And again, in smart grids, we have now different smart components, like you have phasor measurement units and other actuators that communicate wirelessly to the central command. So wireless networks clearly are integrated into smart grids. Intelligent transportation is another example where we are seeing vehicle-to-vehicle communication or vehicle-to-infrastructure communication and so on. And driverless cars, again, it's a very classical example where, so controlling a car, to drive a car, it's clearly a control problem. But to aid the control problem, you have multiple actuators and multiple communication protocols that go into the car. So all these systems, you can broadly also classify them as cyber physical systems, right? Because they have some physical components and they also use communication protocols and computational capabilities. So due to these applications, we saw different results in this field of network control systems. And I'll touch upon some of these results briefly. Okay, so before doing that, let me just describe or just hint at what is the key difference between conventional networks and when you use networks for control applications, right? So the network is the same. You can use the same network for, let's say, sending an email, or you can use the same network for, say, robotic surgery. So what is the difference between these two cases? So these are some of the areas in which these two become very different. So if you look at the primary function, and by the way, this table is taken from this paper. So the primary function for an control network is to control a physical equipment, right? So you want to control a robotic arm, or you want to control a remote drone or something. Whereas for the conventional network, you just want to transmit data, right? So you want to, let's say, send an email or send a file transfer and so on. And if you look at the domains, so industrial applications are clearly used in manufacturing or processing and so on. Whereas conventional networks, like we are doing it right now, they are used in corporate and home environment. So the environment is completely different in these two cases. If you look at hierarchy, then there is a lot of hierarchy in industrial protocols and industrial systems. Whereas in conventional networks, the hierarchy is not that much. It's very shallow. Another important couple of points is severity and the round trip times, right? So let's say if you are controlling or you're driving an autonomous car, and if your network fails, then the consequences can be very devastating, right? Your car can crash into the system. Whereas if you're, let's say, sending an email, and if your network is unavailable, then your email might get sent with a bit of delay, maybe 1 or 2 minutes later. So that's not a big issue. So severity is very, very high in industrial control systems or in cyber-physical systems. Okay, just a second. Yeah. So, and also another important point is the round trip times. So in these control applications, the delay that is required from the network is of the order of microseconds. So around 0.25 milliseconds to 10 milliseconds. Whereas in the conventional networks, you can also tolerate the delays up to 50 or 100 milliseconds. That is also fairly possible. Then we come to determinism. So obviously, if you are using real-time applications over the network, then the network should be available all the time. The reliability should be very high. Whereas in conventional networks, low reliability can also work out. And there are some other points as well. I'll not go through all of them. So this table gives you a picture that if you are using the same network for data transfer, and if you're using the same network for, let's say, any control applications like remote surgery or driving an autonomous car, then things need to be different. You cannot use the same network and the same protocols in both the cases, because these are fundamentally different applications. And that's where this field of network control systems comes into picture. So here we analyze that if we use these networks for control applications, then what needs to be changed and how do we need to change it? So those are the questions that arise in this field. Okay, so with this introduction, this is a brief outline of the talk. So as I suspect that many of you might not have background in control systems, so I'll just briefly go over some introduction on network and linear systems. These are the simplest control systems that you can think of. And then we will see two important results in this field of network control systems. The first is what happens if you want to estimate a remote process over a packet drop channel. And the second one is what happens if you want to stabilize a process over a rate limited channel. And in these two examples, you will clearly see that the results from these two different fields of control and communication nicely come together. And finally, we'll end the talk with some future directions or challenges that are still remaining in this field. And by the way, moving forward, if you have any questions, please interject, and you can unmute yourself and ask you, because that's the whole purpose of this talk. So it's not like a one-on-one communication. So if you have any difficulty in any steps, you can just pause, and I'll pause and I'll answer the questions. Okay? So overall, again, the main emphasis of this talk is to present you that there is a interesting area of network control systems where there's a tight coupling between these two different fields. Okay. All right, so let's begin. So let me start by briefly describing a feedback control systems. I'm sure all of you have already seen this somewhere. So here, let's say if we have a physical system and there are multiple sensors which are sensing different quantities in this physical systems, right? So again, to take an example, you can take a autonomous car, and there are sensors which measures the measurements, the surroundings, the speed and the position and so on, right? Then these sensors send those measurements to a controller. And then the controller uses those measurements to compute the control commands, and then it applies to the actuator, and then the actuator enables the changes in the physical system. So for example, again, in the driverless car, you can say that there is an onboard computer on the car, which is a controller, and it gives the control commands, and then the accelerator or the brake pedals automatically gets actuated to control the car motion. So this is a kind of a feedback loop. Okay. So what happens is that when there is a network present in this feedback loop, so this is the picture. So the sensors now are no longer physically connected to the controller, but they transmit the measurements over some communication network. And similarly, the controller also communicates the control commands over another network. So these two networks can be same or they can be different as well. Now, what happens if there is a network present, right? So as you know, network introduces multiple imperfections. So it can introduce packet drops, it can introduce delays or noises and so on. So then the question arises that if we take this feedback control system, which was operating perfectly without any network, when we introduce a network, then how does the network affect the performance of this whole system? So that is the key question that we'll be looking today. Okay, I hope this setup is clear. Any questions in this setup? Okay, so let me move forward then. So before presenting the results, let me just show you how do we model these physical systems. And I'll just take this very simple example, right? So it's a spring mass system. There is a mass and there is a spring here, and you apply a force in this direction, on the right direction. And then you can clearly write the motion of equation of this spring mass system. It's a ordinary differential equation of second order. And then you can convert this differential equation into this form. And here there are different variables, right? So this x is the state of the system. So z is the position and z dot is the velocity. So you combine z and z dot together and you get x, which we call as the state of the system. So this equation describes how does the state evolve over time, right? So here on the left-hand side, we have x dot, which is the rate of change of the state, and it is proportional or it's linear to the actual state of the system. And this f is the external input to the system. And here y is the output of the system. So for example, if we are only observing the variable z, then y becomes equal to z. So these are the three main components of a control system. There's the internal state of the system, which describes the different variables of the system. There's an external control input, and there's an output of the system. And we can express these linear dynamical systems via these simple equations. So we already saw this first equation in the previous slide. So x dot is ax plus bu and y is c times x. Okay, this is in continuous time. Now we can also write them in discrete time. So the state at time k plus 1 will be a times the state at time k plus b times uk, and y is simply c times xk. And we can also have noises in the system, right? So you take the same discrete time system and then you add some noises wk and vk. So wk is the process noise and vk is the measurement noise. So these noises are typically present in all the systems because you cannot model them perfectly. So if there are noises, then these variables x and y now become random processes because they are evolving over time. Okay, any questions in this modeling part? Are these equations at least clear? So here A, B, C are matrices basically. I'll pause for a few seconds if there is any question. Okay, so let me move ahead. So now, how do you analyze the properties of this system? Okay. So here there are many properties that we can analyze, but here I want to touch upon one property, that is the stability of this system. Right. So here you can see that the state x evolves over time. Right. So now it can happen that the state might go unbounded as time increases. Okay. So because it's kind of an auto regression process, if you can also think it in those terms. So then the question arises, when does this state remains bounded? That is what we roughly call as stability. It's not a very precise definition, but roughly a system is stable when this state of the system remains bounded. It should not go unbounded as time increases. So now the question is, when does the system remain stable? And that depends on the eigenvalues of this matrix A here. Okay. So this is a classical result in control theory. So it says that if you define the spectral radius of this matrix A, so the spectral radius is nothing but the maximum absolute eigenvalue of this matrix A, right? So you find all the eigenvalues of this matrix, and then you take the absolute value, and then you take the maximum of those absolute values. And the result is the following. If the spectral radius is larger than 1, then the system is unstable, meaning that your state will become unbounded as time increases. If the spectral radius is less than 1, then we have a stable system. The state will eventually go to 0 if there are no external inputs. And if the spectral radius is exactly equal to 1, then we have what we call a marginally stable system. So you can have oscillations, or the system can stabilize to some non-zero value. So all these three possibilities are there. So why I'm concerned about stability here? Because we'll use this notion of stability in the next results that I'm going to talk about. Okay, any questions? All right. So now we had a brief overview of these linear systems and stability. Now let's look at two specific problems. The first problem is remote estimation over a packet drop channel. Okay, so let's start with this one. Okay, so here let me describe the problem first. What is the problem that we are looking into? So here we have again a physical system. You can say that this physical system evolves according to these equations. So there's a linear system that is evolving at this location, the blue location. Okay, and the dynamics are governed by this linear equations. We have some noises also here. And then there's some sensor which is measuring some of the measurements. So this yk, the second equation, is the measurement equation. And the first equation is how the system evolves over time. Now, what the sensor is doing, it is transmitting the measurements over a network to a remote estimator. And the goal of the estimator is to reconstruct the estimate of the state that is evolving at this blue location. Okay, so again, to repeat, the goal of the estimator is to estimate the process X that is evolving at this blue location using the measurements that are transmitted over this network. Okay, so that is the simple goal of the estimator. So here the sensor will transmit the measurement yk in each time slot. So we are assuming slotted system. So in each time slot, the sensor will transmit one set of measurements to this estimator over a network. All right, so then let me describe the network model. So here we assume a packet drop channel or a packet drop network in which in each time slot, the packet gets randomly dropped, and the packet drop process can be either IID Bernoulli or Markovian, and other packet drop processes can also be possible. So in this problem, we'll assume that the simplest case that it is IID Bernoulli. So basically, and if you look at the estimator, as I mentioned previously, the goal of the estimator is to compute the estimate x hat k of the process xk using Kalman filter. So I think some of you have already studied Kalman filter, but if not, then it's not super necessary. So it's again, Kalman filter basically computes the minimum mean square estimate of the state using the measurements. So here, let me denote how the performance of the estimator is measured, right? So here we have this matrix PK, which is the error covariance basically between the actual state and the estimated state. So it denotes the estimation error covariance. All right, so with this setup now, the question arises that how does the network affect the estimation performance, right? So clearly this network has some packet drops. So therefore it will degrade the system performance. So we want to analyze that how does this network drops affect this estimation error performance. So the performance of the system is captured by this error covariance, right? Because if the error covariance is small, then the estimator performance is very good. And if the error covariance is large, then the performance is not that good. Okay. Any questions in this overall setup? All right. So then let me move ahead. So we'll make some usual assumptions in this case. So we'll assume that both the noises are IID Gaussian and the packet drop process is IID Bernoulli. So essentially in each time slot, the network can drop a packet with a probability P, and these drops are independent across different time slots. And we'll also assume that this matrix A that drives this physical system is unstable, meaning that the spectral radius is larger than 1. Okay, so these are the assumptions. All right, so now we have this first result that I wanted to touch upon. And this result is from this paper in 2004. Let me explain this result. So it says that there exists a critical probability which we call P of C, such that if the actual drop probability is greater than or equal to PC, then this estimation error covariance PK becomes unbounded. Okay, so if the probability is less than this critical probability, then this estimation error covariance PK remains bounded. And this is again quite intuitive, right? Because if the channel is dropping packets at a very large probability, then your estimation error covariance will become much, much higher, because then the estimator is not receiving any measurements from the sensor, right? So therefore, the error covariance will become very large. And in fact, it becomes unbounded if P is larger than this critical probability. And if P is smaller than this critical probability, then the estimation error covariance will remain bounded. Okay. Now, the important point that I want to highlight here is that this critical probability P of C is related to this spectral radius of this matrix A. In fact, it is inversely proportional to the spectral radius of this matrix A. And the intuitive explanation of this result is that suppose your matrix A has a large spectral radius, meaning that it is highly unstable. So it means that your state is evolving rapidly. However, your network is not transmitting the packets at a sustainable rate. So therefore, your system will become unstable. The error covariance will become unbounded. And vice versa, if the system dynamics is not that fast, if the spectral radius is not that large, then even a smaller success probability is sufficient for this estimation to work out. So here you can clearly see that this notion of drop probability, which is PC, it is clearly a communication concept, right? In communication theory, we regularly deal with packet drop channels. Whereas this notion of spectral radius, it is a control property, right? Because it depends on this matrix A, which is used to describe the control system. So you can clearly see how nicely these two properties come together, and we have this relation in this theorem. So this first result shows that if you want to design your network, then suppose you want to design a network with some drop probability, right? So you cannot just pick any arbitrary drop probability. Your drop probability has to satisfy this condition. So, and this condition depends on the actual control system that you want to estimate. So this shows that the communication and control theories, at least in this problem, cannot be designed independently. They are coupled with each other, right? So if you want to design one, you cannot design it independently. You have to consider the other application, the control application as well. All right. Any questions in this theorem because I'll build up on this theorem later on. So if anything is not clear, you can.
Why do we consider matrix A to be unstable only?
Yeah, so that's a good question. So if the matrix is stable, then basically you don't need to transmit anything, all right? Because if you look at this equation, if the matrix is stable, then the eigenvalues will be less than 1, and then this state X will eventually go to 0. Obviously, there will be some noise, so not exactly 0, but in that case, even if you don't transmit anything, so meaning that even if the drop probability is equal to 1, then also your estimation error covariance will remain bounded. So that is the reason to make this problem more interesting, we make that assumption. Okay, any other questions? All right, I hope this is clear, because I'll build up on this result in the next few slides. So if anything is not clear, you can ask me. All right, so let's move ahead then. So, okay, so now let me present a slightly different variation of the same problem. Okay, so what we call is the remote estimation, but the smart way. So earlier in this previous framework, what the sensor was doing is that it was transmitting the raw measurements over the network, right? But now what we can do is the sensor can become much more smarter. So what the sensor will do is it will compute the local estimates, and then instead of transmitting the measurements, it will transmit the local estimates over the network. Okay, so basically it's receiving the measurements from this physical system, so it will compute the local estimate. So notice that there is no network in this part of the system. So this sensor is receiving perfect measurements from this physical system. So it can compute the local estimate using the Kalman filter. There is no problem here. In this previous case, notice that this estimator was not receiving perfect measurements because some measurements were getting dropped in this network. So here the smart sensor basically computes these local estimates, which it can do without any problems. And then it can transmit this local estimates over a network to the remote estimator. So here you can see that we have introduced some computational capability in this sensor, right? So the sensor is maybe there's some small computer on board which processes these measurements and compute this local estimate. So instead of a naive sensor, we now have a slightly smart sensor, and we'll see how this smart sensor helps us in achieving this goal more efficiently. Okay. All right, so let me then present the result using the smart sensor strategy. So if you use the smart strategy, then this is the result. It's from this paper in 2007. So it says that the error covariance is bounded if and only if your transmission probability is less than this critical probability. And this we again saw in the previous result as well, but the difference here is that this critical probability is exactly equal to this quantity 1 upon rho s square. Okay, so let me go back to the previous result. So in the previous result, you can notice that this critical probability is less than or equal to this quantity, right? So it can be even be lower than this quantity. But in this result, this critical probability PC will be exactly equal to this quantity. And this shows that by using this smart strategy, you can tolerate a much larger drop probability. So this system, this smart system, will be able to give the same performance even under higher drop probability from the network, right? So, and why is this benefit happening? Because we are processing the measurements locally here at the smart sensor level, and then transmitting the local estimates to the estimator. So here the estimator doesn't need to do anything. It doesn't need to compute any estimate. It will just receive the local estimate, and that's it. It will use the local estimate. So that is how the benefit is happening in this case. So here again, you can see that it becomes very important to decide what quantity should you transmit over a network, right? So in the first case, the quantity that we were transmitting were the measurements. But here, the quantity that we are transmitting is a local estimate. So this is in general a very pervasive question in these network control systems. So what should you transmit over a network? So I give you a network, and then the question is, what quantity should you transmit for the network to be most efficient? So here, this is one instance of this general question. All right, so what is the advantage of this smart strategy? As I mentioned, this smart strategy can tolerate a larger drop probability in the network, and it can also work under if there are any packet delays or any reorderings of the packet, then we can use timestamps to make this work. I'll not go into the details of that, but it can be done. Now, what are the drawbacks? So drawbacks is that we need computing resources at the sensor, right? Because this sensor needs to compute a local estimate. So therefore, we need some computational capability at the sensor in this case. In the earlier case, the sensor we can do without any computational capabilities as well. And the second drawback is that we need to transmit a vector of a larger size. So remember this, here we are transmitting a local estimate. So the size of the vector is the size of this vector x. And typically the state vector has a larger size than this output vector. So we need to transmit more data basically in this case. So these are the couple of drawbacks. Okay, any questions in this result? All right, so let me check how much time I have. Okay, so around 20 more minutes. All right. So here, again, this is a slightly different case, but the same framework is there. So here, instead of a single link, we have a network with multiple links. So here you can treat as these gray circles are the routers, and then you have multiple links between these routers. And then finally, we have the estimator. And we assume that the goal is the same. The smart sensor will send the local estimates, and then the goal of the estimator is to compute a remote estimate of the system. So here we again assume that each link in this network will drop packets independently with some probability P of I. Again, this is a simplifying assumption. And here what we define is what we call as a cut set of the network. So if you look at this graph, this dashed line is one such cut set. So it's a cut set is basically dividing the graph into two disjoint parts. And this cut set will involve these 4 edges here, 1, 2, 3, 4. Okay. So the drop probability of a cut set is the product of the probabilities of all the edges that are involved in that cut set, right? So here in this case, 4 edges are involved. This first link, second link, third link, and fourth link. So you multiply all the drop probabilities of these 4 links, and then you get the drop probability of the whole cut set. That is how we define it. Okay. And now there can be multiple cut sets in this network, right? So you can make a cut in this way, or you can make a cut in this way. So you make all the possible cuts, you find all the possible cuts that are possible, and then you take the maximum value of this cut set drop probability, and that we call as Pmax. Okay, I hope this is this quantity is clear. How do we compute it? So now the next result is again for this multiple link case. Again, we have the same result. So again, using the same smart strategy, the error covariance is bounded if and only if this Pmax is less than or equal to 1 upon rho a square. So in all these 3 results, we saw that, again, to recap these results, we saw that there is a fundamental connection between the communication part, which is captured by this drop probability, and the control part, which is captured by this spectral radius of your physical system. And this was one of the first results that basically captured this coupling or this interdependency between these 2 different quantities, the control quantity and the communication quantity. All right. So this completes the first case that I wanted to highlight. Any questions before I move forward to the second case? Okay, so then let's move on to the second problem, which is stabilization over a rate limited channel. Okay, so let me describe that. So again, we have the same feedback system that I mentioned previously. The only difference is that we have a network here between the sensor and the controller, and it's a rate limited channel. So there are no packet drops now. The packets are transmitted perfectly, but you can only transmit a limited number of packets in this channel in per time in each time slot. And between the controller and the actuator, there is no network. So this is a perfect channel here. Okay, and again, the physical system is a linear system that I mentioned previously. The measurements are exactly equal to the state. So this is again one simplifying assumption. So this channel, this green channel, is a noiseless channel with a limited rate of R bits per time slot. So there is no noise, there is no packet drops. It's just that you can only transmit R bits in each time slot in this channel. And the objective here is to stabilize the system. So by stabilize, I mean that we should drive the state of the system to 0. Okay. So here the state is X. So we need to find the control inputs U of K to drive the state X to 0. That is the simple goal. And measurements are equal to the states. So basically the sensor is transmitting the states to the controller, and this controller U of K will then use these measurements to compute a control input to drive the system state to 0. Okay, so that is the overall goal of the system. Okay, I hope this is clear. At least the goal is clear what you want to do in this problem. All right, so now let me make some points about this system. So at the sensor side, we'll have an encoder which will quantize the measurements, right? Because we have a rate limited channel, so we'll have to do some quantization. So this encoder basically uses the measurements and quantizes them and maps them to the R bits that are available for transmission. And the controller will naturally have a decoder, and both of them will know each other's strategy. So the encoder strategy is known at the decoder. And we'll assume that the encoder has memory and the quantization is adaptive. So in each time slot, you can change your quantization levels in response to whatever measurements you are receiving. So it's a non-static case. There are results on encoders without memory as well and with static quantizations as well, but I will not touch upon that in this talk. Okay, so this is the setup, and then let me present the main result straight away. So the result is the following. So remember, we needed to stabilize the system. So this result says that the system is asymptotically stabilizable, meaning that the state will asymptotically go to 0 if and only if this condition is satisfied. So let me explain what this condition is. So on the left hand side, you have the channel capacity or the rates, the bits that are available in per time slot, right? So that was the rate R. So the rate R has to be larger than this quantity. And this quantity is, again, you can see the eigenvalues of the matrix A here. So basically what you do is you take all the unstable eigenvalues. So by unstable eigenvalues, what I mean is that all the eigenvalues whose absolute value is larger than 1. Okay. So you take all those eigenvalues, you take the logarithm, and then you add them. So this quantity on the right hand side is also known as the entropy of your linear system, of the control system, because it determines what is the uncertainty in the control system that is evolving over time. So this sort of captures the uncertainty in the control system, the entropy, and the result then simply says that in order to stabilize the system, your communication rate R should be larger than the inherent entropy of the system. And this is famously, it's a very famous result, it's known as a data rate theorem in the network control systems literature. And again, you can clearly see that here this rate R is clearly a communication concept, right? We naturally see it in information theory, and we deal with this limited rate channels all the time in communication and information theory. Whereas the right-hand side, probably you haven't seen in communication theory at all, because it's a control theory concept, right? Again, the eigenvalues of a matrix A capture the behavior of the control system or the physical system. And when you bring these two together, you can clearly see that this data rate theorem, it's a nice combination of these two different diverse fields. The first time I saw this result, I immediately recalled another famous result in information theory, right? So in the information theory, we have this result that data can be transmitted with an arbitrary low errors if the rate R is less than the channel capacity. So this is sort of a counterpart to this this theorem in information theory, which is the data rate theorem in network control systems. And this result, although we did not consider noises here, but this result is also valid for stochastic systems when we have noises present in the system. And there, instead of this definition of asymptotic stability, we'll have the mean square stability by taking expectations over the noises. Okay, any questions in this mean result? I hope at least this equation is clear to you what this equation says. If not, then you can ask me. I'll pause for a few seconds. Okay, so
why are you, just one question.
Yes.
Why are we considering only the network between sensor and controller, not the network between controller and actuator?
Yes, so that is only for this talk I have considered it, but there are other papers which have considered the rate limited channel in this portion as well. Yeah, so I have not included those results because again, those are a bit more advanced results. So typically when there is a channel between the controller and the actuator, analyzing that part is slightly more difficult than analyzing this part between sensor and the controller. Yeah, but there are results, and you can refer to those papers if you are interested in them.
Thanks.
Okay, any other questions? All right, so then let me just wrap this up. So we haven't considered other imperfections in the network part, right? So there can be sampling delays in the network. There can be transmission delays also in the network. If you are using a wireless channel, there can be network access delays, right? So how all these delays will affect the performance of the control system, that I haven't covered. The channels can be noisy as well. We haven't considered noise in the previous two cases. And then there is a pervasive question of what data to send over the network and when to send it. So all these questions are out there in this field, and these are some of the questions have been answered, some are open currently as well. So this is just to let you know that there are many more things in this field. We have only touched upon two specific cases. Okay, so now let's come to the last part. So I'll just briefly describe some of the future directions that are possible or that haven't been looked into in this field. So if this talk, maybe if this interests you, then you can take a look at these directions, and maybe if you want to work on this, that is also that you can take it up. Okay, so I think I have 5 or 6 more minutes. So I'll wrap it up, and then I'll be open to Q&As. Okay. So In the previous cases, what we saw is that we only had a single feedback loop, right? So if you remember the feedback loop, we had one physical system, one controller, and then sensors and encoder and decoders. But in reality, we can have multiple such feedback loops over a single network. Okay. So, and there can be multiple applications also. So you can use the same network for, let's say, driving a car or flying a drone or something else, right? So a single network can be used for multiple applications, and there can be multiple feedback loops present over the same network. So then a very interesting and challenging question is that how do you support these heterogeneous applications or these different types of systems on a single network, right? Because if you develop some protocols or some algorithms for one specific type of systems, they might not work for a different type of system. Then the challenge is that how can you develop these in a modular fashion such that using only a single network, you are able to support all these diverse applications. And we'll also need to manage or prioritize traffics from these different feedback loops in this case. So again, there have been some works, but there are multiple questions that are still remaining in this scenario where we have diverse applications and diverse feedback loops in the system. Okay. The second broad direction that I want to comment on is the core design of control and communication strategies. Right. So, for example, if you look at the sampling strategy, so we saw that the sensor was transmitting the measurements in each time slot, but it need not be that way. So it can be time driven. So for example, you can do a periodic transmission. So instead of transmitting in every slot, you can say I'll transmit only in 10 time slots or 20 time slots. Or it can be event driven also. It's again a very exciting different field on is that some event that happens only when then you transmit your measurements, right? So for example, if you're driving a car and if you are changing a lane, let's say, and if you deviate very largely from the normal position, only then you control your car. Before that, you might not bother to control the car. So there is some event which triggers, and in response, you do the sampling or you do the control. And then there are, as I mentioned previously, there are multiple types of delays that are possible, right? So when you do sampling of the system, you can do sampling with some delays. If there is access problems, like if you're using wireless MAC protocols, there is an access delay. There's a transmission delay, queuing delay, and also delay in computing things. So all these delays are there, and it's a challenge to analyze or to make sure that your system is working correctly in presence of these delays. There can be dropouts as well. So suppose your controller is not receiving any measurements. So then what do you do? So for that, we need to develop some intelligent open loop algorithms, right? So let's say your car is not receiving any measurements from the camera on board. Then what should the car do, right? So one possibility is that the car should slow down, or it should come to a rest because it's not sure how to drive at a very high speed. So those sort of intelligent open loop algorithms are also an exciting problem area. And then naturally, if we have these wireless devices, there is a energy usage constraints also all the time. So if you want lower delays or if you want lower dropouts, then we'll have to use more energy. So there's always a trade-off between these parameters and the energy used by these sensors or actuators. So all these core design problems are again open in this field. Okay. Okay, moving next, wireless networks, control over wireless networks. Again, it's a very, very new area, and it's a very interesting area that a lot of people are working on it. So again, there are, as you might know, wireless networks bring their own extra challenges in the system. So you can have fading, you can have interference, you can have range issues, and all those things will happen if you use wireless networks, especially for control applications. So there are some existing standards that deal specifically with industrial control problems. And there are standards like wireless HART and others, which are based on Bluetooth, Zigbee, and WLAN standards. So there definitely have been work in this area, but a lot of problems are still open. So because wireless systems bring their own convenience, you can put the wireless transmitter receivers anywhere. You don't require physical wiring and so on. But then there are these challenges as well. And as I mentioned previously, if a wireless link fails for, let's say, transmitting an email, that is still fine. But if a wireless link fails for, let's say, driving a car or let's say driving a robot, then the car and the robot can crash. So ensuring reliability in this wireless scenario is even more challenging for these control or cyber physical systems. And then again, there are different questions on, we have been using these different algorithms, right? So you have this MAC protocols, you have TCP/IP routing protocols, you have different scheduling protocols for these purely communication systems. But when you use these communication networks for these control applications, then we need to rethink, can we change the routing protocol? Can we change the MAC access protocol for these specific applications? Because we need to do that. If you blindly use the existing protocols for these control applications, then this will not perform well. So again, this is a very pertinent question to developing new protocols for this type of cyber physical systems. And one again interesting problem is security of these systems, right? So again, since there are these communication channels, these computational components, so there is always a problem of hacking into these systems. And if there is a malicious attacker that attacks the system, then it can cause a lot of harm. And we have seen these examples, right? So in power grids, security is a very challenging problem. So what happened that initially these control systems were standalone applications, right? So they were isolated from external world. But now we are coupling them with communication channels or computational systems. So they are no longer a standalone or separate entities. They are connected entities. And this connectedness brings new security problems. So for example, if you use conventional networks into these systems, then if there are any vulnerabilities in the conventional networks, these systems will also have those vulnerabilities. And if we use open protocols in managing these systems, then if there are any weaknesses in these open protocols, then these systems will also be weak against those kind of vulnerabilities. So therefore, while we are making these systems more and more intelligent, right, we are introducing communication components, we are introducing machine learning algorithms and computational features. So all these are making these systems more intelligent. Again, a classical example is a driverless car. But on the flip side, these systems are becoming less and less secure as well. So therefore, we need to give priority to security of these systems as well. So this is again a very hot topic of how to make these systems secure while making them more intelligent. Okay, so we should take a look at both of these sides of the same coin. Okay, and there are many others. I'll not go into the other details, but there can be a possibility of distributed decision making and control problems, right? So should we make local decisions in these systems, or should we make global decisions, what to transmit and when to transmit? I touched upon this previously as well. And how to operate these systems intelligently in open loop and other sampling, smart sampling and transmission-based strategies are possible. Okay, so I think, yeah, I'm done with my presentation. These are some references in case you are interested in some of these problems, or if something is not clear, you can take a look at some of these papers. So again, to conclude, the goal of this talk was to give you an overview of this. I'm not sure whether you were aware of this field of network control systems before, but the goal was to give you an overview of how nicely these two separate theories of communication control systems can come together. And we have some interesting results, and we saw a couple of results in this talk. And moving forward, as you can see, that the systems are becoming much more complex. Right? So it's no longer possible to design these theories independently. So moving forward, we need to couple the communication theory with control theory and bring in signal processing and machine learning as well. Because these complex systems are again composed of different components, different types of components. So we need tools and techniques from these different diverse domains to build up these systems. And that's where this field of control systems can really help. Okay, so thank you for listening patiently, and I'll be happy to take any questions. Hello, am I audible, Pritam?
Yeah. Are there any questions on the chat? I don't see any specific queries posted. So if there are no questions, then let's thank Professor Vaibhav for a fantastic talk. Actually, I think he gave a nice overview of this domain, starting from the basics till the latest research challenges. So let's thank him, and we will continue with the lecture sessions tomorrow. So those who have registered only for the lecture sessions, we'll see you tomorrow. And those who have registered for the lab sessions, we have already sent you invites for registration for the lab. And please register on those link and set a password for accessing the lab resources. And you'll be able to follow the instructions from there on. We also sent you an invite for registering on a discussion forum for the lab session. And there is please note that there is a separate Zoom meeting invite for attending the lab sessions in the afternoon. So you'll need to join using that separate link. There's a separate link. So the lecture sessions link will resume from tomorrow. You can use the same link tomorrow morning for attending the lectures. And those who are joining the lab, see you at 2 o'clock. And please complete the registration and password setting by that time. So thank you so much, and thanks, Professor Vaibhav.
Yeah, thank you.